8. So today we're going to begin talking about alkanes and conformational analysis. And I sent a couple of videos out Sunday afternoon. Hopefully you had a chance to watch them. We're going to deal with both cyclic and acyclic alkanes. So let's start with acyclic. That term just means that it's not a ring. Right, we're going to start with acyclic alkanes. So that would be something like this, right? Just a simple chain. We're going to start out with ethane, which is a 2-carbon alkane. And we're also going to look at cyclic alkanes. Right, and we're going to focus more on 6-member rings, like cyclohexane. And we're going to talk about the different conformations of both, right? Cyclohexane actually doesn't exist as a flat molecule. It exists in a what we call a chair conformation. We'll talk about that. And for acyclic alkanes, we're going to talk about Newman projections. Right? We kind of touched this a little bit before, but we're going to go into more detail with it now. I wish I had my model kit, but I don't. I intended to bring it so I could have it to build some of these models and display them, but I apologize for that. But I'll have it on Wednesday. All right. So with the acyclic alkanes, we're going to start out with some basic ideas about the conformations of those alkanes, because a lot of times we get kind of lulled to sleep thinking that everything is static, and it's really not. So any alkane, I'm just going to start with ethane. Right, the most basic. Well, it's not the most basic. Methane is the most basic, but you can't do a Newman projection with that. Right, ethane is here, and then we take ethane and think about this in terms of its 3D structure or 3D orientation. Right, each one of those carbons is a tetrahedron. So the 3 H's are actually have a little bit of 3D orientation, where the one here on the dash is going back into the page. Right, the one on the wedge is coming out of the page. And we've had some experience talking a little bit about stereochemistry, and it's the same thing here. Right. So if we were to turn that entire molecule kind of back into the page, what we would see is something that looks like this. Let me zoom in on that. So this carbon will be here. This one will be here, and we see something that kind of looks like this. Right, if we turn the molecule that I have drawn in 3D if this is the plane here, sorry about that. Wrong button. If this is the plane here and we kind of rotate it around this way, right? We see this, which is what we call a sawhorse. Everybody's seen this before, right? You on a construction site, you see like what they call a horse. So basically a 2x4 with legs on each end, kind of like this. They use it to they put it underneath like pieces of plywood or whatever, so they can cut it. They'll have a stable surface to cut on. So that's why it's called a sawhorse, right? So this gives rise to what we call a Newman projection, right? And what that is let's say that, and I remember explaining this a couple of weeks ago, but let's say this is this carbon is we're going to call carbon 1, and then the back carbon the other carbon we'll call carbon 2. We're going to give it a different color. Right, so the Newman projection is actually taking that carbon-carbon bond and looking straight down it. So looking from the perspective of 1 straight down the bond, right, to carbon 2. So carbon 1 is going to be in front. So I'm going to make this will be carbon 2. Let's go ahead and fill that in. And then carbon 1 is going to be here. Right? Don't worry about the size difference and all that. They're both the same size, but it's easier to show the Newman projection if we draw it like this, right? So I'm gonna put the hydrogens back in. So on carbon 1, I got a hydrogen here. I got 1 here, and I got 1 here. And then on carbon 2, on the back carbon, I got the same thing. So I got a hydrogen here. I got 1 here and 1 here, right? So this particular Newman projection all right, this is a model that we use to talk about a couple of things. We use it to talk about what we call conformational mobility. In other words, rotation around carbon-carbon bonds. And we use it to talk about, in the same vein, stability, like how stable one conformation is when you compare it to another. So we're going to take this Newman projection, I'm going to copy it, and I'm going to add another page, because now we can talk about the energy associated with this Newman projection. All right, so let me just copy that. Any questions so far?
So the sawhorse, are you looking from like the side? Or
Slightly. You're looking at an angle. You're looking from an angle, not like dead on from the side, because that's what we see up top with the wedges and dashes. But if you were looking at a slight angle, like let's say you were looking at from the perspective of standing exactly in front of this hydrogen, then you will see what the sawhorse would look like.
okay.
Good question. Nope. And copy. Sorry. All right, so let's take this down, and we're going to use this as the basis for our discussion on conformational mobility. So let's talk about that. All right, so when you have a ethane molecule like this one, right? There's a problem with this particular conformation. We call this the Eclipse conformation. You should have seen this in the video if you watched it. And this is redundant, but it's okay to be redundant. We're gonna just walk this down and talk about the energetics. And then we're going to take that same information and apply it to chairs when we start talking about chairs, because it's really a very similar type of information. All right, so this is the eclipse conformation. All the hydrogens are overlapping. So if you would really look, I had to draw it this way so you can see everything, but if you were really looking at this in a model, like the hydrogens would be right on top of each other, right? So this hydrogen here and this one here, they're overlapping. And that's not good, because each one of those interactions costs energy, right? So for that, those two hydrogens to overlap with one another like that, can somebody tell me how much it costs for one hydrogen overlapping interaction? If you watched the video last night or yesterday at some point,
I can't remember if it was 1 or 4 kilojoules per mole.
it costs 4 kilojoules per mole. I heard somebody else say it too. For that to overlap. Now let's think about that. There are 3 sites that are overlapping, right? So it's going to be 4 for each one. Right? What's the total it's going to cost me for this to stay like this, stay in the eclipse conformation?
12 kilojoules.
Say that again.
12 kilojoules per mole.
12 kilojoules per mole. That's a lot of energy, right? And so to alleviate that strain, which in this case is torsional strain, the hydrogens are not big enough to cause steric strain. We're going to look at propane and butane to talk about steric strain. But in order to alleviate that, the carbon-carbon bond here that you see up here, right? We can rotate around it, right? So it's just like turning a dial on a radio. Well, y'all don't have dials, y'all got buttons now, but or turning a dial on the stove or oven or whatever. All that's out too. Well, not the stove top. But fortunately, they still have dials on them, so it makes some sense. But turning a dial, right, it's the same thing that you're going to do here. So normally, when I want to draw the other conformer, I do it by only rotating one of the carbons. So I'm either going to rotate the front or the back. So what I want to do is I want to rotate the front carbon. I'm going to rotate in this direction. Let me change the color of that. So I want to rotate so that the hydrogens aren't overlapping anymore, if that makes sense. So I'm going to delete these hydrogens. Hopefully I won't delete that back carbon. And now I'm going to draw this in a different conformation. So now this is hydrogen here, and hydrogen here. This is what we call what? Anybody? Staggered conformation, right? And that comes from rotating around the carbon-carbon single bonds. Again, this is a carbon-carbon single bond. I can rotate around that bond to get to a more stable conformation. That's the whole idea behind the term conformational mobility, because everything in the universe is trying to go from a less stable to a more stable state, right? It's that simple. So now what I've done in rotating around the bond is I've increased the angle between the hydrogens. Now this is what I call my dihedral angle. is 60 degrees now between those hydrogens. Right up here, the dihedral angle is 0 degrees between the hydrogens. All right. So anytime I need to get to another conformation, I can do it by rotating around the carbon-carbon bond. All right. And I want my staggered conformation is always going to be the most stable conformation. All right. So staggered is better than eclipsed. And so in a Newman projection, that's what you're trying to get to. You try the Newman projection allows me to show the different conformations, whereas I couldn't see that if I just look here, right, at the 3D conformation or at the sawhorse. I can't see that. But the Newman projection allows me to see what it looks like when I rotate around the carbon-carbon bond and increase the angle or decrease the angle, right? Because I can go back to staggered if I just, and I'm going to do this real quick just to show you, just to make a point. So these 3 hydrogens right here, when I rotate again, I'm continuing to rotate, and I'm rotating it clockwise. All right. So I'm just going to rotate again clockwise that way. And what happens, again, let me erase these. Actually, you know what? I can keep them. What happens when I rotate clockwise is now that hydrogen that I had highlighted in green is now here. The one I had highlighted in blue is here. And the one I had highlighted in brown is here. Can y'all see that? So again, I'm rotating clockwise, and I closed up the dihedral angle, now back to 0. So now I'm back to an eclipse conformation. And I'm back to the energy of 12 kilojoules per mole. Right? Anybody not following or not grasping it?
I have a question.
Go ahead.
Well, never mind. Hold on. Wait. You said you rotated clockwise.
Mm-hmm.
Oh, I see it. Okay.
All right.
So the staggered conformation has the lowest energy, but it's the most stable, correct?
Yes.
Okay.
So you said, but that the lowest energy and most stable go together. So instead of but, it will be and. You understand what I'm saying? It's the lowest energy conformation and it's the most stable conformation for ethane.
Okay.
Right? When we look at butane, which is another molecule that has more substituents, then we'll see that there are some staggered conformations that are higher in energy than others, but there's at least one that's the lowest out of all of them. All right. So this is, let me take that back. Now let's look at propane. We're going to look at propane because for ethane, it's just going to keep oscillating between eclipsed and staggered. Right. So it's not going to change anything. You're going to go from 0 energy, which is, well, relatively 0. Nothing is ever really 0. All right. But we're going to say 0 kilojoules per mole. relative to the other ones, right? But there's nothing is ever zero because there's always movement, there's always vibration. So you're always going to have some energy associated with a molecule. It's not static, and there's really no real way to depict that because everything we're looking at is in the book unless we look at a simulation. There's no real way to depict that other than to ingrain it in your mind that nothing is static. There's always vibration, there's always stretching, movement of the bonds, everything. So yeah, so let's take this up to another molecule. Let's look at propane. All right, so propane is a 3-carbon chain. And I'll put the methyl groups in like so. All right. So we pick when we want to draw a Newman projection, we pick. We're either going to do these 2 carbons right here, or we'll do these 2 carbons. You always have to pick which carbon bond you're looking down, right? So it doesn't matter which one we pick, we're going to get the same thing. So we're going to take this and we're going to do just what we did down below. We're going to make the CH3 the front carbon. So I'm going to make that in green. And then the back carbon, we're going to do a different color. Should have done that in reverse. So that's one of my carbons. And then the other carbon I'm going to do here. All right. So let's start out. All right, let's start out staggered, because on the energy surface, you can see that this starts out staggered. So I'm going to start it out staggered, but I'm going to put the H's in first. And then I'm going to put on the back carbon. Notice I got 2 hydrogens and I have a methyl group. So I'm going to put the methyl group here, right? So this group is going to be attached to the back carbon. This is going to be that purple carbon, right? So I'm going to put the methyl group here. And then the hydrogens here and here. All right, and again, when we look at this, what we're doing is we're going to pick a carbon to rotate. We're going to rotate the back carbon or the front carbon, right? So what in this case, let's rotate, and let me do something here because this has, I want to make it match this, but it doesn't have to. We can work around that because it actually made the middle carbon the front carbon. We'll work around it. All right. So now we got a problem right here because again, this is all this causing energy, right? When it's eclipsing, this is 4 kilojoules per mole. This is 4 kilojoules per mole. And then based on the energy right here, 14, how much does it cost for the methyl and the hydrogen to overlap like that? If that's 8 and the total energy is 14, how much does that methyl hydrogen overlap cost?
6.
6. Good. So 6 kilojoules per mole. All right. So that's a total of 14. So that is going to represent, actually, you know what? We're going to wipe these out. Instead of being confusing about what's where, we're going to just white them out and put in what we have. White now, get out of here. Is that all right? Everybody okay with that?
Yeah.
All right. Okay. So now let's go to here. This is gonna be our Newman projection that we start out with right here. So I'm gonna move this. And we're gonna rotate, we're gonna again continue by rotating the front carbon. So this goes here. Anybody disagree with that? It costs 4 kilojoules per mole for each hydrogen overlap. And this is propane. Let me put that up here. So when you go back and look at this, if you go back and look at it, you'll know what we're working on. So that's that, right? And if I rotate, notice how the energy oscillates. If I rotate around 60 degrees clockwise, and I'm going to rotate, since we started out rotating, what we do on the front? We were doing the front carbon, right? Yeah. So if I rotate that front carbon around 60 degrees, I'm going clockwise. I'm rotating in this direction. What is the staggered conformation down here in this energy well going to look like? Anybody?
It's gonna be staggered.
Yeah, it's going to be staggered. So let me just redraw this. I have the luxury of being able to cheat. It's over to. All right, so I'm going to put this here. I'm going to put this here. And I'm going to put this here like that. I'm going to shrink that down. Right, does that alleviate the steric strain that well, not the steric strain. Yeah, the steric strain between the methyl and the hydrogen?
Yeah.
Call me class all the time. All right. So now we've alleviated that by doing what? Conformational mobility, rotating around the carbon-carbon bond to alleviate that strain. So this is effectively zero. That's why you see it all the way down that well. And if we did it again, right? Not that we would want to, but just for the sake of understanding what's happening, if we rotate again 60 degrees, what is that going to do? What conformation will we have up here? And let me color them again. So that's going to be green. This is purple, and this will be.
Would it be eclipsed?
Yes, you'll go back to being eclipsed. Telling me, oh, it's going to the back. Shucks. Hold up, I got a trick for that. Yeah, it'll go back to being eclipsed. And where would that yellow hydrogen end up?
Would it be on the top left?
I'm gonna put it here in this well, because when I put that white writing over that, it kind of screwed it up. So think about it. We're going 60 degrees clockwise, so everything is going this way, right? So the yellow hydrogen actually ends up here. And then the green hydrogen ends up where we at? Here. And then the purple hydrogen is here. Here. Right? Following? All we're doing is taking that front carbon and turning it like a dial. We're turning it around, and every turn is 60 degrees.
I have a question.
Go ahead.
Before we were working with ethane, so like 2 carbons. Now we're working with propane, and I get confused. So the H3C, what is that exactly like showing?
Oh, that's just a convention. You're talking about how I have it written up here?
Yes, yeah.
Yeah, it's just a convention. Sometimes if I write that like this, and there may be some compulsion to believe that it's actually the hydrogen that's connected to this middle carbon. So just by convention, I write it backwards so that you'll know that it's a carbon-carbon bond and not a carbon-hydrogen bond. So it's not,
Okay.
it's just semantical. It's not anything special or esoteric about it.
Okay, because I was trying to see, like, I guess the 3 carbons, I guess, on this from the Newman projection. I was getting confused.
Yeah, so it's right here, right? So that's a great question. This is one carbon right here. Let me see what I can do here to highlight this. This is a carbon. Is that right? And then that carbon is bound to the carbon here shown in purple, the big carbon in the back, which is bound to the carbon here, the little green dot. So that's a 3 carbon chain.
Okay, so that's
Yeah.
why you had to put the carbons on the side. Okay, that makes sense.
Yeah. And let me show you, I'm glad you said that, because we could, this, doing this for propane, it's not going to change anything, right? I want to do butane because you get a lot, there are other conformations that you have to think about. But here, you're just going to keep oscillating between staggered and eclipsed, and it's just going to be a methyl overlap with hydrogen and eclipsed, and then it's going to be alleviated in the staggered. All right, but let's go to, let me show you, that's a great question. So let's look at something like this, right? This is a Newman projection. And the thing is, here's the Newman part right here, right? This is the front carbon. And then the big circle behind it is the back carbon. You following?
Yes.
So this is not a terminal. It's not at the end of a chain. It's in the middle of a chain, which is fine. You can do that. But the thing about it is, when I look at the chain itself, that's a 9-carbon chain, right? Because the front, these 2 carbons are connected. So if I wanted to take that and turn it into a skeletal structure, I could just draw that out like this. Is 9 carbons. So that's 8 strokes. And then if I look here, if I start numbering from here, 1, 2, 3, 4, 5, right? I'll see that on carbon 5, 1, 2, 3, 4, 5, there's a methyl group. Because you can see in the Newman projection, there's a CH3 attached to that carbon that's depicted as the back carbon. You're following that? So the Newman projection is between these 2 carbons right here, this one and this one.
I have a question.
Go ahead.
So the methyl is on the back carbon. Okay.
So the huge circle is, I guess, the back carbon. Is what?
Yeah. So if I took this chain and looked down these 2 carbons right here that I have highlighted in purple, this is what I would see as a Newman projection. Well, one conformation of the Newman projection. So when we talk about propane, which we were doing up here, right? It's kind of similar, right? You got the only difference is the end of the chain, the terminus is where we start because we don't have any other carbons to attach to that. But we will see that with butane, which is here on this particular energy surface. And you can see there are a lot of different energies. So there are a lot of different conformers that we have to think about, but really the only ones that are the important ones are here, 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 and here, because everything else is going to be it's just repeat. Like once you go from 0 to 60 to 120 to 180, everything after that just repeats. So let's look at it. So this is the potential energy surface for butane. Which looks like this, right? It's a 4-carbon chain. Right, if I want to write it out, it's CH3, CH2, and I'm not writing, I'm just writing this. Right. So normally for butane, the Newman projection is shown between the 2 central carbons. All right, so we're going to try to follow the energy surface. So with that conformer at 19 kilojoules per mole, let's see what that looks like. So we're going to draw, let me see if I can, let's keep that. I can use that. Right, so we're going to take this and on the front carbon and the back carbon, we're going to have, this is going to be H, and this is CH3, and this is CH3. All right. So that's the first conformation based on the potential energy surface. Are y'all following that? See how high that energy is, 19 kilojoules per mole? So that we got to account for that. So we're going to start there. So here, let me move this over. How much does it cost for each of the hydrogens to overlap?
4.4
kilojoules.
4. And if the total is 19, how much does that make the methyl overlap, which is a really, really serious steric interaction. So this is a steric interaction. If you watch the video, then you should know that a steric interaction is when the groups are large enough to touch, the substituents are large enough to touch one another. So that really increases the energy. That's bad. All right. So how much would that make that worth if the total energy is 19 kilojoules per mole?
11.
11. Good. So 11 kilojoules per mole. All right. So that's my conformer at 19 kilojoules per mole, right? I'm gonna paste this up there. Right. So there's another really important, and Sanaya, can you see here where this is carbon 1, the purple dot is 2, that's 3, and that's 4. So it's kind of like you're looking at it like this, the chain like that.
Yeah, I can see it.
Mm-hmm. So you can really draw Newman projection for any alkane. Doesn't matter how long the chain is, just pick 2 carbons, and then whatever is attached, it is what it is. All right. So let's go back to here, and I'm gonna copy this. I'll take these numbers off though. I can't. Yes, I can. I just want to do it. So I don't want to erase it because then it'll erase everything. So I'm gonna put this up top. So this is the conformation that costs us 19 kilojoules per mole. right? That methyl-methyl overlap is an intense steric interaction, and it costs a lot of energy. 11 kilojoules per mole that's a lot of energy. All right. What can I do to alleviate it? What do we do with all the other conformations when we wanted to alleviate some bad interaction?
You can rotate.
Rotate around the carbon-carbon bond. So let's take the front carbon and we're going to rotate again clockwise. So everything is going clockwise, right? Every group on that carbon is going to get rotated around. So then if I draw that conformation, this is eclipsed, am I right? The first one on the left. Is that eclipsed?
Yes.
It is,
Yeah.
right? So my next conformation has to be what? Staggered. Following? Yes, no? So if I rotate around 60 degrees from this conformation, I get to here, I'm here. This is not only staggered, but there's a special name for it. And it's gauche. Right? Because these two groups, although they are 60 degrees to one another, they still have a little bit of an interaction because of their size. So this costs, the gauche interaction costs 3.8 kilojoules per mole. And that is the structure that is here at that point on the energy surface. All right, questions about that? So just even though the angle between them is 60 degrees and you have alleviated, much of the strain that was there when the angle was 0, it still costs some energy for them to be staggered to each other like that. All right. What's my next conformation going to look like?
Eclipse.
Eclipse again. All right, so if I go again, rotate it this way, 60 degrees all the way around. That's going to give me another eclipse conformation. The only difference is now my methyl groups are going to be in different places. So this is going to be hydrogen, that's hydrogen, and that's methyl. You can see that the methyl is coming around to that position. So this is what? 6, 6, and 4, right? So that's the conformer at 16 kilojoules per mole, which is right there. All right, so let me cut this in or copy it and paste it up there. So on the energy surface, that's what we're going to put here. And let me put the ghost one up there too.
I have a question.
Go right ahead.
It's about the 6 kilojoules per mole.
Yes.
Is that between, like, I know it's between the dihedral angle, but like for the one we just did, like, is it between the hydrogen on the front carbon and one of the hydrogens on the methyl group?
Yeah, so this interaction right here is 6. It's the methyl hydrogen overlap. See how there's a methyl group there, and there's also a methyl group back here. Right, and it's overlapping with a hydrogen here. And because you got a methyl basically on both the front and the back carbons, you're going to have that. So it costs 6 kilojoules per mole for those to overlap like that.
Oh,
You said it's still called Eclipse, even though I guess
Yeah.
different things are
Yeah.
overlapping.
Yeah, it's still eclipsed. There's no special name for this particular one, right? All we're looking at now is how much each interaction costs. And then the final most stable out of all of your conformers is this one, because I'm going to rotate again 60 degrees clockwise. So I'm going to come to another staggered conformation. To be this one, right? What, anybody remember what that's called based on what was in the video?
is it anti?
Yes.
Oh,
Right, and that what that means is that there's a 180-degree angle between your methyl groups. And you can see that here, right? They are 180 degrees apart from one another. That's the most stable. That's the one that's here in the well with a energy of relatively zero. Put that there, right? This is the anti-conformation. So with butane, you have a couple of specialized terms that you have to remember, which is gauche, which is a staggered conformation where your two methyls are 60 degrees to one another, and then anti, where the two methyls are 180 degrees from one another. All right, any questions about this or about anything we talked about?